So now that we've done solids of revolutions using disk and washers, what we want to now do is the shell method. Now the point of the shell method is that maybe you can't solve for one of the variables, but you want to slice that way anyway. Like maybe you want to slice vertically, but you can't solve for y. Or maybe you want to slice horizontally, but you can't solve for x. Well, that's going to be a problem, and that's why we use the shell method. So like I was saying, you want to use the shell method whenever you have a problem and you need to solve for the other variable. So let's say that you want to slice vertically. Well, ideally, you would want to solve for y. Because if you slice vertically, you want the integral to be some sort of function of x here and then dx. But let's say that you can't solve for y, well then you're going to have to use a shell method. Or let's say that you want to slice horizontally. Then ideally you would have to solve for x equals some sort of function of y. Then our integral would look some sort of function with y as your variable and then a dy. But if you can't solve for x, then you're going to have to use the shell method. So basically how this works is that in one direction, you're going to get disk and washers. So maybe if you slice vertically, that's what you're going to get. The other direction is going to give you a shell. And what a shell looks like is it's the shell of a cylinder. So disk and washers in one direction. If you slice the other direction, that's how you get a shell. And a shell just means the shell of a cylinder. So let me just show what I'm actually doing here, which is jumping into an example. So my area is going to be bounded by y equals 1 over x. And then we're also going to have y equals 0, x equals 1, and x equals 2. And we're going to rotate this about the y-axis. So just like we did before, first thing I'm going to do is I'm going to draw this region. So 1 over x is this curve. There's another part of this curve down here in the third quadrant, but I'm not going to draw that because it's bounded by y equals 0, which is the x-axis, and also x equals 1 and x equals 2. So here's x equals 1, and here's x equals 2. Okay, so there's our region. I am rotating this about the y-axis. So I'm going to kind of treat that like a mirror.
Hello, Mama.
Draw this other line here. All right. So I think here's kind of our picture. It's kind of weird. So it's almost like maybe the bottom of a Christmas tree, kind of with a hole in the middle. Kind of hard to tell, but anyway, you can see that the way I've drawn this, I've kind of drawn this like I'm slicing horizontally. I mean, that's how I drew these circles, is that they hit the y-axis. So I'm slicing it horizontally, and that gives me these washers. The issue is, if I sliced, and let me get a different color so that I don't mess up my picture. If I take slices up here, well, those have different bounds than slices down here, right? These upper ones have these two bounds, and these lower ones have these two bounds. I don't really want to have two different integrals. So what I can do is, instead of slicing horizontally, and that's going to give me a washer, which I've already done, I'm instead going to slice vertically. And let me put this in maybe a purple color. So if I slice vertically, what you want to imagine is this slice completing the revolution. So if this slice was being revolved around the y-axis, it would kind of go out of your paper, and then it would go back in, and it would give us this cylinder. So that one slice Here was my slice. We imagined what that would do if I actually did the rotation, and that gave us this cylinder. So what we're going to do is we are going to integrate the surface area of this cylinder. Now, the surface area of this cylinder actually just looks like a rectangle. I mean, if you imagine taking this, almost like the label off of a can, like if you have a soup can and you take the label off of it, it looks like a rectangle. Okay, and that rectangle, of course, has a little bit of depth. Because we sliced vertically, our little bit of depth is going to be delta x. As far as the area of this goes, well, it's just length times width, or base times height. As far as what this length is, that's the circumference of a circle, which is 2 pi times the radius. So what we're going to do is we are going to find the volume of a slice, just like we did before. I know it's going to be 2 pi times the radius, that was the length, times the height. So I'll go ahead and change this to just be height. So 2 pi, I'm going to leave that radius alone for just a second. If I go back up to my picture, what was the height of this slice that I took? So here was the height, I'll put little arrows on it. Well, that height was given by just the curve 1 over x. So that's my height. And then we have this delta x. Next, I need to figure out what was the radius. Well, the radius was being measured from the y-axis all the way out towards that slice, which is just whatever the x value was. I mean, if the x value was 1.5, so let's say my slice was right here, then the radius would be 1.5. If my x value was 1, then the radius is 1. It's just whatever the x value is. So there's your volume of a slice. So now we'll have our integral. It's going to be 2 pi times x times 1 over x, and of course those are going to cancel. I'm just writing this out. You need to decide, where did I start taking slices and where did I stop taking slices? And since this is in terms of x, go from left to right. So start here, go left to right. I start taking slices at 1, I stop at 2. So just simplifying this, I have the integral from 1 to 2 of 2 pi dx, because the x and the 1 over x, of course, they cancel. If I integrate this, I get 2 pi x from 1 to 2, which should give me 4 pi minus 2 pi, which is 2 pi. So there's your first example of a shell method. Do a couple more of these. So next, let's let my area be y is 1 over x, y is 0, x equals 1, x equals 2. It's that same area as before, only now I'm going to rotate this about the line x equals -1. As far as my picture goes, it's kind of the same. Right, I still have this curve. Here's x equals 1, there's x equals 2. But now we're going to rotate this about the line x equals -1. So pretend now that's your mirror. The only difference between this one and the last one is that you have a bigger hole in the middle of our solid. So there is our picture. You can imagine this kind of comes out of the page and then back through. It's that same picture as before, it's just a bigger hole in the mirror. Now the way I've drawn it, like I said, when I drew these curves, I was slicing horizontally. So I kind of want to slice horizontally. The only problem is that slices here versus slices down here have different bounds, so I'll have to have 2 different integrals. So I don't really want to do that. What I'm going to do instead is, like we did before, slice vertically. So let's take a slice vertically right here. Imagine that it makes the revolution. So it made this revolution, it went out of the page, back through the page. It looks like this really wide cylinder. We're going to figure out the volume of the slice, and then we'll integrate from 1 to 2. Now the volume of a slice, because this was a cylinder, it was 2 pi r times the height, and then for us, delta x, because we were slicing vertically. I'm not going to worry about the radius for just a second. We're going to worry about the height. So back up here in my picture, the height is going from the x-axis up to this curve. So it looks like my height is still 1 over x. Now let me get a different color to show you the radius. Let's go with green. So now my radius, though, is being measured from over here at the line, x equals -1, all the way to where that slice was. And the question is, what is that? Well, I know that the distance x goes from the y-axis over to that slice. And I know that this distance is 1. So it looks like my radius is x plus 1. So the integral we're going to do, this color isn't great for showing up, go to a darker green. I already know that I'm going to go from 1 to 2. That was my original picture, and that hasn't changed. Only now we're integrating 2 pi x plus 1 times 1 over x dx. And if you want to do this, you would probably multiply through, and we'll get 2 pi plus 2 pi x dx. So I'm simplifying the integral before I do it. Then I'll take an antiderivative, so I get 2 pi x plus 2 pi natural log of x, because the antiderivative of 1 over x is natural log. This is from 1 to 2. Then you can plug in the 1 and 2. I got 10.369 for mine. Okay, next I'm going to look at y equals x squared, y equals 0, x equals 1. And let's rotate this about the x-axis. Now, if I were you, and this is just a suggestion, I would pause right here, and I would try to figure out that volume by yourself. What I'm going to do is, first thing, let's draw this picture. So y equals x squared, y equals 0, x equals 1. It looks like my picture is going to be this kind of almost a triangle, but the hypotenuse is a curve. So there was y equals x squared, that's the curve, y equals 0 was my x-axis, and then x equals 1. And we're rotating that about the y-axis. So it looks a lot like a dog's watering bowl or a dog's feed bowl. It has kind of these 90-degree edges, but it has a like a cone in the middle taken out. Now, of course, you could do this using washers and discs. I think that would be fine. Because I want to get in the habit of using a shell, let's use this shell. So I'm going to take a vertical slice, and I know that a vertical slice gives me shells because this circle that I just drew, that was slicing horizontally. So slicing horizontally gave me circles or washers, which means that slicing vertically is going to give me a shell. All right, so there's my shell. We're going to look at the volume of a slice, which is 2 pi r times the height, and then for us, delta x, because we're slicing vertically. For my radius, because we're measuring from the y-axis, my radius is just from the y-axis out to my slice, which is x. We're not adding anything to it like last time. For my height, that's being measured from the x-axis up to the curve. So that gives me an x squared, and then my delta x. So the total volume will be going from 0 to 1. We're integrating 2 pi x cubed dx, which you can work this out on your own. I got pi over 2 for that one. Now, what I did say is that you could integrate this, or you could slice this horizontally. That's totally fine. Let me show you how you would do that though. So I'm just going to redraw this picture. So I have kind of this bowl, the 90-degree edges. Let's say that we're taking a slice horizontally. So if I take a slice horizontally, it looks like a washer. So the volume of my slice now looks like it's going to be pi times my big radius squared minus pi times my little radius squared, and now delta y, because we're slicing this horizontally. To figure out the big radius and then the small radius, subtract, and we should get the same answer. So in my picture, let me change colors so we can do the big radius. My big radius is from the y-axis all the way out to that line, and that line was where x equaled 1. So it looks like the volume of a slice is pi times 1 squared minus, and then we need to figure out our little radius. So my little radius is going from the y-axis out to this curve. The issue is that curve is put in terms of x, and we can't do that, so we need to solve for y. So pi times the square root of y squared, and then delta y. So for our integral, looks like it's going to be pi times 1 squared, which is pi, minus pi times the square root of y squared, so pi times y. But now as far as our bounds go, we're looking at the y-axis now. So it looks like it starts at 0. We stop adding up at this point right here, which is where y equals 1. And I know that's where y equals 1 because it's on the curve y equals x squared. And if x is equal to 1, that means that y was also equal to 1. So you should get the same answer either way, just two different ways to do the same problem. Do whatever makes sense to you, though. I want to do one more. I know this is getting to be kind of a long lecture, but the first one I want to do is x equals 1 plus y squared, x equals 0, y equals 1, y equals 2, and my revolving line is the x-axis. I'm just going to set this integral up. I'm not actually going to solve it. I think that setting up the integral is the hardest part, so keep that in mind. So first off, when I just look at this problem, before I even draw it, when I'm looking at this problem and I know it's a solid revolution, because this equation is in terms of y, right, because it says x equals something, that makes me think that I would like to slice horizontally. And the reason I would kind of like to slice horizontally is because I won't have to rearrange this and get y by itself. So that's just some key things to look for. If it's in terms of y, which this is, then you probably want to slice horizontally. If it was an equation, let's say it was y equals 1 plus x squared, well, that would make me think I should slice vertically because it's in terms of x. Doesn't always work, but that's just kind of a good thing to look for. So back to this, x equals 1 plus y squared is a parabola that's been put on its side. X equals 0, that is the y-axis, and then y equals 1, and y equals 2. So there's my picture, it's just this top part up here. And we are revolving that around the x-axis. So it's almost like that picture we had before, it's just been rotated 90 degrees. And like I said, I would like to slice horizontally. Now I know that if I slice vertically, I'm going to get washers and disc. That means if I slice horizontally, we are looking at a shell. So follow the path of that slice, and let's see what it looks like. So there's my slice. We're going to figure out the volume of a slice, which is, since it's a shell, 2 pi r times the height. For us now, delta y. I'll leave the radius alone for just a second and deal with the height of a slice. So the height of my slice, and I'm going to put this in red, The height of my slice is going from the y-axis out towards the curve. So there's the height of it. Looks like it's just that curve, 1 plus y squared. Next, and I'll put this in green, we need to look for the radius of this cylinder. So the radius is going from the x-axis up to the slice. And since it's going from the x-axis, it's not adding or subtracting a number, just y. So my integral is going to be 2 pi y times 1 plus y squared dy. Where do we start adding up these slices? At 1. We stop at 2. Those are a few examples of integrating using the shell method.